So we talked about calorimetry and measuring things at a constant volume. So now we're going to talk about what we can do at constant pressure. Constant pressure is easier to achieve practically because if the chemical reaction is open to the atmosphere, then it will be at constant pressure. But when that happens, energy can evolve as both heat and work. Remember, the work is P delta V. But often we only care about the heat evolved. We know that there's some work happening through volume expansion, but we just really don't care about that. So we have another quantity called enthalpy, and it has the symbol capital H. And enthalpy is the sum of the internal energy and the product of the pressure and volume. So internal energy plus pressure times volume. That's the definition of enthalpy. So enthalpy is also a state function. Doesn't depend on how you got there, only where you started and where you end up. Internal energy, pressure, and volume are also state functions. So we can look at the enthalpy change, delta H, as the heat evolved in a reaction at constant pressure. So if we take that H equals E plus PV, and we throw some deltas in there, the change in heat is equal to the change in energy plus P times the change in volume. We didn't say change in pressure because this is at constant pressure. And so we're just going to leave the pressure alone there. Yes?
Does that mean that if the pressure could change, then either volume or energy would have to stay the same? Like if you move the delta in front of the P and you just removed it from in front of the volume, would the proportion be the same, right?
So, yeah, if you have honestly, I can't think of the answer to that question right now. I am sure that there is another permutation of this that talks about that, yeah. The change in pressure with constant volume, that's where we were looking at the work or not having work with the constant volume calorimetry. So delta E, change in internal energy, is the heat evolved plus the work. So here we're using QP to indicate this is heat at constant pressure. And then P delta V is P delta V. Well, work, pressure volume work, is negative P delta V. So then negative W is equal to P delta V. So for this P delta V, we can substitute in negative W. So then we've got delta H is equal to the heat evolved at constant pressure plus W minus W. So those go away, and the enthalpy change equals the heat at constant pressure. Now that is not the same as the energy because we have made the work go away and the change in internal energy is still heat plus work. So it's not that there's no work being done, it's just that we can subtract it from itself and make it go away. This is, math voodoo kind of stuff. And so the change in enthalpy is not exactly the same as the change in energy. Enthalpy change is the heat at constant pressure. But delta H and delta E are very similar in concept. In fact, it's a bit hard even for me. I have to really think about it. Well, okay, what exactly is the difference between these two things? And they are often very similar in value. And so for Chem 1A, we can just kind of treat them as the same thing. You can say, yeah, I know there's something different about them, but practically we use them the same way, so we can just kind of not worry about it. The delta E is a measure of all the energy, heat, and work that get exchanged between the system and the surroundings, and delta H is only looking at the heat exchanged under constant pressure. The only time this difference becomes significant is if you have a reaction that produces a large amount of gas, so you get a big volume change, or something that uses up a large volume of gas, again, with the big volume change. But that's not usually what happens. Usually any volume changes are quite small, and so the work thing is not really significant. So a conceptual question. Lighters are usually fueled by butane. When 1 mole of butane burns at constant pressure, it produces 2,658 kilojoules of heat and does 3 kilojoules of work. That work would be pressure changing volume against a pressure. What are the values of delta H and delta E for the combustion of 1 mole of butane? So I just told you don't have to worry about the difference, and now I'm asking you about the difference. Well, let's identify these numbers that we were given. 2,658 kilojoules, that's heat, right? So that's Q. And the work is 3 kilojoules. And then we have to think about what are the signs of those numbers. It says the reaction produces this many kilojoules. Is that going out from the system or coming into the system? It's going out. When money goes out of your bank account, that's negative. So this is a negative. And it says the reaction does 3 kilojoules of heat. I'm sorry, does 3 kilojoules of work. Does 3 kilojoules of work. So you do work or you have work done for you. Doing work is negative. Having someone do the work for you is positive, right? So this is also negative. And identifying those signs just kind of requires a bit of just thinking about it. So then delta H and delta E, if you look back through the slides, delta E was Q plus W. And delta H well, it was delta E plus P delta V, or it's just Q at constant pressure. So kind of just putting down some things that I know, and then looking over here at the multiple choice answers. And so my choices for delta H are negative 2658 or positive 2658. And we already decided that this is a negative. So we can cross off that last choice because we know that delta H is wrong. So then delta E. Well, delta E is a little easier to deal with than this messy stuff. Here, delta E, we're looking at Q and W added together. So the first choice, delta E, is 2655. Well, what do I get if I take minus 2658 and minus 3? I get minus 2661, right? These two guys added together is minus 2661. So this would be if I took the Q and subtracted the work or had the sign wrong on the work. So that's wrong. And here, this one's saying that delta E is just the work. That's also wrong. And so it must be C, and it is C. So a multiple choice question, a lot of times students like multiple choice questions because it's like, well, I can at least answer all the questions, right? But some of the answers can be very misleading, and so students sometimes do worse on a multiple choice exam. But you can also use these choices to help you narrow stuff down even when you don't completely understand what's going on with the question. right? It's like this one, if you had to do it without any choices given, you might struggle with that, right? It's like, I can't remember. But here we can look at, like with the delta H, we could figure out the sign on Q, and so we could just eliminate this one down there. And so we can start eliminating some things. And those are test-taking strategies. Now, is that necessarily really knowing your chemistry? No. But to make use of that test-taking strategy, you're using some chemistry knowledge. And so that's not cheating or anything. Go ahead and use test-taking strategies. Any questions? Oh, that's the answer, C. It's like, what is there a C up there for? I wrote the slides, and I don't remember what's on there. Okay, so the signs of delta H and delta E follow the same conventions. They are both energy, right? Changes in energy. So when delta H is positive, heat is being absorbed by the system. Heat is going into the system. So thermal refers to heat, right? This is heat. And endo is like the word into. And that's what it means, into or inside. So endothermic is heat going into the reaction, into the system. Heat being released by the system. Exo is like exit, which means to go out. Okay? So endothermic heat coming in, exothermic heat going out. I think the trickiest thing here, though, is to identify what is the system. Because there's the system and the surroundings. One's endothermic, one's exothermic. Heat's just being transferred, and so you have to identify which side you're on. It's kind of a little bit like looking at both sides of a situation. There's a bad side and a good side. So chemical cold packs often contain ammonium nitrate. And when that ammonium nitrate dissolves in water, it is an endothermic process, and the solution gets cold. So your skin, which would be part of the surroundings, gets colder because the reaction in the cold pack is absorbing heat. So oftentimes the reaction is the system. The system here is not the cold pack. The water is not really part of the reaction. The plastic on the outside is not part of the reaction. The reaction is this kind of intangible thing happening that you can't put your finger on. You can't measure the temperature of the reaction, because how? How could you even do that? You can measure the temperature of the immediate surroundings, though, which would be the cold pack. So the cold pack is absorbing heat, but the cold pack's getting cold, right? So you kind of would think, well, if something's absorbing heat, it's going to get warmer, right? But the heat is going into the chemical reaction. The heat is being transformed into stored chemical energy.
So would you say that the plastic surrounding the cold pack is, the molecules are vibrating because they're absorbing energy, right?
Well, the plastic around that is part of the surroundings, and it's just getting warmer or colder, like the air and your skin and anything else around it.
So if you could measure how much the molecules are vibrating based on the energy that's being absorbed, could you determine the rate of absorption?
Could you determine the rate of heat absorption? I suppose you could. You know, and it'd be really great. Do you guys remember the Magic School Bus? Yeah, it was a great TV show. Some really great science stuff, right? I was always jealous, though, because they could get in this bus and they could zoom down and they could be the size of a red blood cell or something, right? It was like, we could do so much stuff if we could do that. You could zoom down, and if we could look at the ammonium ions and the nitrate ions and look at how much they're vibrating, we could then measure their temperature. But the thing that's happening here is not that the ammonium and nitrate molecules are getting hotter. It's that they're forming bonds that use energy. And so the heat energy gets transformed into stored chemical energy. Like dropping a marker, right? Here it's got potential energy, and when I drop it, it goes faster and faster as it goes down until it hits the floor. The potential energy, which is related to its elevation above the floor, is going down, but the speed is going up. The energy is changing form. And so that's what happens to this heat energy when it gets absorbed by a reaction. It's changing into a different form of energy. It's not heat anymore. Yeah.
So with the ammonium nitrate, would that be the system?
Yeah, the reaction of the ammonium nitrate interacting with water would be the system. Yeah. Chemical hand warmers, like we talked about way back at the beginning of this chapter, with the iron filings that react with oxygen. That's an exothermic reaction. It releases heat. Now, the iron filings and the oxygen weren't hot to start with. It's not that they gave you the heat, but they had stored chemical energy. And when they react, that gets released as heat, and the heat flows to things that are lower temperature. So their exothermic reaction, the surroundings get warm because the reaction is releasing heat. And combustion reactions like burning natural gas, another example of exothermic reaction. There's energy coming out of the reaction. It's not being created. It's just being transformed from one kind to another. There's energy coming out and being transferred to the surroundings as heat. Yes?
So the heat packs are also not the system. The stuff inside is the system.
The chemical reaction would be the system. Yeah.
And then the stuff around it, whatever that is the
surroundings.
Thank you.
But you can define it any way you want.
Okay. But that's the easiest.
But that's what we typically are doing when we're calculating all this stuff. Identify each process as endothermic or exothermic. Now, these are not necessarily chemical reactions, and we can identify endothermic or exothermic processes where we can change the answer depending on what we define as the system. So what's a little bit tricky, like on an exam, and I try to be careful with those questions, is I try to make it obvious what the system is supposed to be. These questions might not be as obvious. So an ice cube melting. So there's only one thing mentioned here, right? It's the ice cube. Now, if you have an ice cube melting in your hand, you could treat your hand as the system and the ice cube as part of the surroundings, but there's no mention of a hand here, right? The system is the ice cube. So when the ice cube is melting, is it absorbing heat or is it releasing heat? It's absorbing heat, right? There's a couple of ways to think about that. Think about, well, if I touch the ice cube, does my hand get colder? Yes, it does. So that means my hand is losing heat. The ice cube must be gaining the heat, right? An ice cube melting, you can also think of, well, what can I do with heat that would make this go faster? Well, I could stick this in a pot on a stove and put a bunch of heat into it and it would melt a lot faster. Well, there's another clue. This is an endothermic process, because if I put more heat in, it happens more quickly. So this is endothermic for the ice cube. And so what's the sign on delta H? Is delta H greater than 0 or less than 0? It is greater than 0 because the ice cube is getting energy. Yeah. It's positive for the ice cube. If it's in my hand, it's negative for my hand, but it's positive for the ice cube. Okay, nail polish remover quickly evaporating after it's accidentally spilled on the skin. So nail polish remover generally contains acetone, and you can buy stuff, nail polish remover that is straight acetone. Ooh, it's cold, right? Anybody want to try? You two people, I just sprayed acetone in my hand. It's cold. Just like when you get an immunization and they rub your skin with a little alcohol wipe. it feels cold. Why does it feel cold to me? Because heat is leaving my hand, and where's it going? To the acetone to cause the acetone to evaporate. So for my hand, that's exothermic, because I'm losing heat, but for the nail polish remover, it's gaining heat. So this question does mention nail polish remover and skin, but what seems to be the main subject of this sentence? It's the nail polish remover, right? So I would interpret this as the nail polish remover being the system. So the nail polish remover quickly evaporating. For the nail polish remover, that's going to be endothermic. And if it's endothermic, then delta H is greater than 0. So this is another state change. So with a state change here, we're going from a liquid to a gas. If it helps you to answer a question like this, you can generalize it to any other state change that you're familiar with. It's like, well, I don't know about acetone, but I know what happens with water. If I want water to evaporate, to go into the gas state, do I make it hotter or colder? Hotter, right? You got a wet towel that you want dry. You put it in the dryer blows hot air on it because that makes the process happen faster because the process is endothermic. So if we put heat into it, it'll happen better. Gasoline burning within the cylinder of an automobile engine. Exothermic. So this requires a little bit of knowledge, either chemical or life. Life knowledge says, yeah, when that happens, the engine gets hot and I better not touch it, right? Where did all that heat come from? The chemical reaction. A little bit comes from friction, but most of it's from the little explosions happening in the pistons. So that's exothermic. Here again, gasoline burning in the engine, the gasoline is intended to be the system. So you could also answer this based on chemical knowledge, having no idea what's going on with an automobile engine. Something burning. That's a combustion reaction. Combustion reactions are always exothermic. So anytime something's burning, or you see combustion, or you've got this thing reacting with oxygen, it's going to be exothermic. So then what's the sign on delta H? It's negative. Less than 0. Because the gasoline is losing heat. So this is like many things where we've got exothermic, endothermic, positive, negative, and it can be very confusing. And I recommend that you just learn to think about the process because it is abstract, but it's not really that strange. And if you just stop and think about it, it's not so bad. Yeah.
I wanted to ask, the 0 you're putting down represents temperature?
The 0 represents change in energy.
Okay,
So is the change in energy, is it getting more energy or getting less energy?
I just wanted to clarify.
Yeah.
Like I thought you said it's less than 0, and I didn't know.
Yeah, it doesn't, the temperature would probably either be, for an endothermic reaction, the temperature of the surroundings would go up. Go down. Go down, I think about that. And for an exothermic reaction, the temperature of the surroundings would increase because of the heat being transferred. But the delta H is really measuring the heat that's being transferred. So exothermic reaction gives off thermal energy. Where does that come from? I kind of already gave this one away. The internal energy of a substance is equal to its kinetic energy plus its potential energy. Kinetic energy can't be the source of this energy that's being given off. Because if that were the case, then in this exothermic reaction, the temperature of the system would fall, it would decrease. as the kinetic energy is being released. So it doesn't, right? So it's the potential energy is the source of this energy that's being released. When the atoms rearrange in the chemical reaction, their potential energy gets converted into thermal energy. So like in the burning of gasoline, you have weak carbon-hydrogen bonds that get broken, and that absorbs a little bit of energy. And that's why a combustion reaction like that typically requires a little burst of energy to get it started, like a spark. And then strong bonds between carbon and oxygen and hydrogen and oxygen get formed. And when strong bonds form, it releases a tremendous amount of energy. Because it's a little bit like two things that are attracted by a strong magnetic field, right? They go like bang together, right? And they're like really happy to make this bond, and it releases energy. Breaking a bond always requires energy to break the bond, but a weak bond only requires a little bit of energy. And if you make a bond and break a bond and make a bond and break a bond, it's just a back and forth process, and the energy change has to be the same both ways. So a weak bond takes a little bit of energy to break. When you make that weak bond, a little bit of energy gets released. A strong bond, you have to put a lot of energy into it to break it, to get those things apart. And then the opposite, which is harder to understand, is when that bond forms, it releases that same amount of energy it required to break it. So there's a lot of things here that the one way is really hard to think about, and so think about the opposite way, and that's easier. Mm-hmm.
Could a exponentially large endothermic reaction physically pull things towards it? Like I understand it takes the association between energy and matter, but since it's absorbing so much energy, could it actually draw things to it?
I don't think an exothermic reaction, even very vigorous, could endothermic. Okay, I don't think it could actually pull stuff towards it. I don't think it could do that. But you've got some really great ideas. You got some really great questions. So in an exothermic reaction, we have weak bonds that get broken and strong bonds get formed. In an endothermic reaction, strong bonds are broken and weak bonds are formed. So when the energy is getting sucked in, the heat is getting sucked away from your hand, say in that cold pack, what's happening is the weak bonds that were present, the strong bonds that were present are getting broken. And the energy is getting pulled in to break those bonds. And they make new bonds that give off a little bit of energy, but the net result is that it absorbed a lot of energy. The question of how fast that process occurs, about whether it happens spontaneously or not, those are much larger, more complicated questions for another class. An endothermic reaction occurs in a flask. What happens to the temperature of the flask? So the reaction's endothermic, so what's the reaction doing? It's sucking in energy, right? The flask isn't part of the reaction, but the flask is near the reaction because this is happening in the flask. So the reaction is sucking in energy. That means the flask is losing energy, right? So does the temperature of the flask rise, fall, or remain unchanged? It will fall. That makes sense? Did you guys have problems with that pre-lab question?
How is it falling?
So the reaction is absorbing energy and that energy is going into breaking strong bonds. And so the energy comes from the surroundings as thermal energy or heat. And so when the flask loses thermal energy, its temperature goes down. It's really neat when you can get your mind around it and actually understand it. And then you kind of have to keep reviewing it because you can say, oh, wow, that's really cool. And then it can just slip away and be gone. But it's some really neat stuff. So, stoichiometry again. Comes back over and over and over again. I told you it was a big deal. So, the enthalpy change for a chemical reaction, enthalpy change is delta H. And so we call this delta H RXN because we get tired of writing the word reaction. So delta H for the reaction is called the enthalpy of reaction, or often called the heat of reaction, which makes the H kind of make sense. So this is an extensive property, meaning it depends on how much stuff there is. So the amount of heat transferred depends on the amounts of reactants that actually react. So if you take a drop of gasoline and burn it, or you take a gallon of gasoline and burn it, are you going to get a different amount of heat being released? Sure, right? More gasoline, more energy, right? So delta H depends on how much stuff there is that's reacting. So by convention, we write delta H reaction in relationship to a balanced chemical equation. And it's written for the number of moles of reactants in the equation. So as this is written here, this guy right here, we get this amount of energy being released for 1 mole of propane, 5 moles of oxygen being used, or 3 moles of CO2 being formed, or 4 moles of water being formed. So the delta H here refers to the molar amounts in the chemical reaction. That saves us from having to write per mole or per gram of this or that or the other thing. Okay, and so this is a very useful conversion factor to use in stoichiometry. We can use it to convert between moles and kilojoules. So let's look at this thermochemical equation. A thermochemical equation has the energy specified. I'm wondering now if I typed this in wrong or what, because 2A is going to AA. Shouldn't it be A2? I don't know. Anyway, that's the reaction. And when 2 moles of A react, the heat that we see is negative 51 joules. So 51 joules of heat energy is released when 2 moles of A react. So the question is, what's the heat associated with the reaction of 6 moles? How do you make 2 into 6? Times 3. So if you're using 3 times as much stuff, it should make sense that you're going to get 3 times as much energy, right? Which one of these numbers is 3 times minus 51? C. The writing it out showing your work method would be, I've got 6 moles of A, and I'm trying to convert to joules. I'm going to divide by moles of A, and then from this thermochemical equation, there's 2 moles of A for negative 51.0 joules. The moles of A cancel out, and you get minus 153 joules. Okay, does that make sense? Ammonia reacts with oxygen according to this equation. Calculate the heat in kilojoules associated with the complete reaction of 155 grams of ammonia. So we have a chemical reaction, and we have a mass, 155 grams of ammonia. So let's write that in here. 155 grams of this. And then they're asking for the amount of something else. Those are the hallmarks of stoichiometry. You got a chemical reaction, you have information about one thing, and you need to find information about a different substance. Here, the different substance is energy rather than a product or something. So for stoichiometry, we start with grams to moles to moles to grams. And sometimes that's what we need, and sometimes we just need to change up the ends a little bit. Can we start with grams of something? Yeah, we've got 155 grams of ammonia, and we could go to moles of ammonia. But then at the end, are we trying to find a mass of something? No. What are we trying to find? Kilojoules. So the kilojoules, minus 906 kilojoules, this number relates to any of these. So I don't have to go from moles of ammonia to moles of something else and then to kilojoules. I can go directly from moles of ammonia to kilojoules. So there's still moles in the middle, but this time it's only one, not instead of two. We don't have a mole ratio between two substances. I have this mole ratio between delta H and the moles of this. So 155 grams of ammonia. I'm going to convert that to moles. Divide by grams. And then I can go directly to kilojoules and divide by moles of ammonia. And again, the units are going to tell me what to do. So that first term, I need the molar mass of ammonia, and just to save time, no, that's something else. I don't know where that came from. It's 17.034. And this kilojoules per mole, I get that from the heat of reaction. That gives me the kilojoules minus 906. And this is per 4 moles of ammonia. So then I just have to multiply and divide. 155 divided by 17.034 times negative 906 divided by 4, negative 2061.0 kilojoules. I should have 3 significant figures on that. So I can round that to minus 2060 kilojoules. It's not 206, or what's safer is to put it in scientific notation, because then we get rid of that confusing 0 at the end. Any questions? Minus 2.06 times 10^3. Okay, so here's one going the other way. What mass of butane in grams is necessary to produce 1.5 times 10 to the third kilojoules of heat? And then as a side question, what mass of CO2 is produced? So this is stoichiometry again. I'm going to write the 1.5 times 10 to the 3 kilojoules over here with the delta H. And then the question is grams of butane. That's this guy, grams. And if you don't know that that's butane, I would certainly understand that, but you should know that the other ones in that equation are not butane, right? Process of elimination. So stoichiometry, because we have amounts of different substances, different things, and we've got a chemical equation. Grams to moles to grams. Am I starting with grams this time? No. Am I ending with grams? Yes. So I'm trying to get to grams of butane over here. And so I have to have moles in here, so I'm going to need this guy. But then what am I starting with? I'm not starting with grams, I'm starting with kilojoules. I could go kilojoules of energy to like moles of CO2 and then to moles of butane, but it's completely unnecessary. I can go directly from kilojoules to moles of butane. So I don't need either of those steps. .5 times 10 to the third kilojoules. I'm going to convert that to moles of butane. So kilojoules come down there, so those are going to cancel out. And then I'm going to convert that to grams of butane and divide by moles. So delta H says minus 2658 kilojoules for every 1 mole of butane. So 1 mole of butane minus 2658 kilojoules. And then I need the molar mass of butane, 4 times 12.01 plus 10 times 1.008, 58.12.
Would that be 1 mole or 2 moles because you have the fractional coefficient for oxygen?
That's a good question. So this equation's weird because there's a 13 halves in here, right? So normally we don't use fractional coefficients, and so we'd say, well, we should multiply everything by 2. If we multiply everything by 2, then we multiply this by 2 also. This refers to the molar amounts in the equation as written, whether it's regular form lowest whole numbers or not. Just however it's written. Good question. So 1.5 EE3 divided by negative 2658 times 58.12 gives me a mass of negative 32.799 grams. What is wrong with that? How can you have a negative mass? You can't. So that means we screwed something up. Mm-hmm.
So you're using the amount of energy that was removed.
Mm-hmm.
So doesn't that mean that the mass of the object would be absorbing energy? So wouldn't it be the opposite sign?
Well,
Like,
the reaction is giving off energy, right? And here we're talking about producing, the reaction is producing this amount of heat.
yeah.
So the reaction is losing it.
Yeah, but that means the mass is gaining it?
No,
No? Or is the
it
mass
means
gonna-
that this number is negative. So this 1.5 times 10 to the third is negative because the reaction is losing that amount of heat. And if I put negative 1.5 and divide by negative, then I end up with a positive mass. You just can't have negative
No,
mass.
that's not what I was asking. Like, that's what I did, but I just kind of skipped the determining that it was a negative in the energy by knowing the masses.
Yeah, there's two ways to approach this. One is to be very careful in labeling things that are negative. The other approach is to say, well, I'm just going to leave out all the negative signs and do the math, and then I'm going to look at the answer and decide what its sign should be. So if you just leave out all the negative signs, you'll end up with a positive mass, and you say, well, is that how it should be? Yeah, that's how it should be. On that previous example where we ended up with kilojoules, and if it comes out positive, then you have to say, well, if it's being produced, it should be negative. And so then you deal with that. Yes? I changed it to negative because the problem is saying that the reaction is producing this amount of heat. So the reaction is losing the heat. And when we look at delta H, we see that that's also negative because when this reaction occurs, heat leaves the reaction. So both of those are negative. You can't have one be negative and one be positive, and unless you switch the order of the reaction, switch it to run backwards, and then you switch the sign on delta H anyway, so they're always going to be the same sign. Yeah.
So can we assume that if they give us delta H with negative joules, then the amount of joules, like in the problem, should be negative? Is that fair to assume?
Yes. So here, delta H is negative because this is an exothermic reaction.
Right.
So the only way you could have a an amount of energy that was not less than 0 is if you had nothing reacting, then you'd have 0. But you can't have this reaction occur and get a positive Q. Yeah. 33 grams. I'm going to skip the other part because, it's nice and everything, but we don't have much time.